Hi there, this is Waves Lesson 7. This one's refraction. It's mainly just information. You should be able to draw and label refraction diagrams and identify what happens to light when it enters materials of different densities. So here's an example of refraction. So as you can see, that doesn't look right. There's obviously something happening. So basically water is obviously a different density to air, and glass is a different density again. So when light travels through from one medium to another, by medium I mean substance, so substance such as air or glass or water, there's a change in wave speed and the light changes direction, so you can sometimes get images like this. This looks like an extreme example of refraction, so let's move on and see. So you can kind of link refraction to aquaplaning. So aquaplaning is a phenomenon where cars' tire gets slowed down by water on a road. So essentially, you might drive through a puddle, or a big puddle. A couple of your wheels slow down. Obviously, your other wheels still going the same speed, so you get a change in direction. Similar thing happens with light. So this is a classic example. So we've got a ray box firing a beam of light out. It's glass, which is a different density, refracts, which means it changes direction, and then refracts again as it enters back into the air. So when a wave enters a more dense medium, it slows down. And when a wave slows down, it changes direction, and we call that refraction. Remember to pause at any point if you want to make any notes. So refraction occurs when a wave passes across a boundary, at which the wave changes speed. This is a wave slowing down on crossing a media boundary. Media or medium is just substance or material. So the change of speed usually but not always results in the direction of travel of the wave changing. So the only exception is when light travels to a surface at 90 degrees. And I've got a diagram that I'll be doing some sketching on, and I'll show you what that means later. Right, so refraction of light. So this is less to more optical or optically dense transition. So this is from air to glass. So glass is obviously more dense than air. So what happens is the light will refract towards the normal in that instance. So here's another example. So as you can see, it's changing direction, coming towards the normal. So the normal, it's obviously, so if it didn't change direction, it'd obviously go in that direction, but it's moving towards the normal in that direction. So light bends towards the normal. The angle of refraction is less than the angle of incidence. So the angle of incidence is this one, and the angle of refraction for the red one is this one. And for the orange line, that is the angle of incidence that we measure from the normal, and the angle of refraction is from the light to the normal. So when it goes into more dense media, it refracts towards the normal. And then the opposite, if it goes into a less dense medium, refracts away from the normal. So light bends away from the normal, the angle of refraction is greater than the angle of incidence. So this is an example that you might see. So I call this limo. So limo just stands for less in, more out. So the angle gets less as it goes in, more as it goes out. So I'm just going to label this up here. So this first one, that could be called the incident ray. So incident, you would have a normal on the boundaries. So like this, that should be at 90 degrees. That would be the angle of incidence. Just extend this down a bit. So this is the angle of refraction. You'll notice that the angles are always measured from the normal. And then on the way out, another normal. That could be called the angle of emergence. So that's the incident ray, the first one. The second one would be the refracted ray. And the last one you could call the emergent ray. Right, what I said earlier is that light, when it hits a different medium, will change direction unless it's at 90 degrees to the surface. So for example, if we had a normal here and we shined the light directly down the normal at 90 degrees, the wave would just slow down. So there'd be no change in direction. It'd carry on in the same direction, it'd just be moving slower. And we can link this back to the wave equation. So the wave equation is wave speed is equal to frequency times wavelength. V equals F lambda. So in this example, when it goes from air into glass, the wave speed will go down. The wavelength decreases as well, so this goes down. The frequency stays the same. So that is from air into glass, obviously because glass is more dense. As it comes from glass into air, so I'll write the wave equation again, the wave speed will go back up and the wavelength will increase. The frequency stays the same. So during refraction, I can make a note on this one. Did I say diffraction? I meant refraction. During refraction, frequency stays the same. So that's it, relatively short one. That's refraction. Hopefully that's okay. And thanks for watching.